Dear students, let us resume back our discussion on sampling rate conversion of discrete time signal. I am sharing the screen here. So let us continue our discussion on sampling rate conversion of a discrete time signal. Now let us summarize the discussion that we had in the previous class, and then let us see how does this impact in the frequency domain, in the sampling rate conversions. Okay, so yeah. So what we have seen is, if we have a discrete signal x of n, then we can downsample by m factor, m times, by a factor of m, and represent this as x downsample signal, x of m into n. Okay, and the implication is t dash, the time period will increase by mt for the downsample signal. Okay, similarly the frequency is decreases by m times. Okay, that means the number of samples per second when these time period and frequency are with reference to corresponding continuous time signal like c of t or xs of t. Okay, these are from okay, xc of t or xs of t, underlying x of n. Okay, so from where x of n has got, from there we are trying to say this. Okay, so that's what is the frequency will decrease because the time period is increasing. That means the number of samples per second will decrease when the duration of samples that we sample increases. This is referred to as downsampling. Okay, and we have seen how to do this on some of the simpler examples in time domain, right? We'll see its implication in the frequency domain now. Similarly, when x of n is upsampled by m times, by L times. Okay, we are just trying to take different notation for upsampling just to distinguish it better. We write it as upsampled signal or expanded signal as x of n by L. So the implication for this is t dash, the time period will change by t by L. That means we are trying to sample closely. Okay, or similarly f dash, the corresponding frequency, okay, of sampling will increase by L times. Okay, we are sampling, we are getting more number of samples per second, L times more number of samples per second. Okay, this is again referred from, okay, continuous corresponding xc of t or xs of t, underlying x of n. Okay, so now let us see. We also have discussed that these upsampling is usually followed by interpolation, because upsampling process creates zeros in between. Okay, our expansion process creates zeros in between, because in the discrete signal, if you see, we don't have any information in between the samples. While in the continuous signal, if you want to depict what would have been there in continuous signal, there should be an interpolation process that we should use. Okay, we will see that later. But for time being, let us represent this x e of n 0 else. Sorry, 0 else. Okay, this is for what? For n equal to plus or minus k times L. Okay, so else 0 else. So when the index of the expanded signal is multiple of capital L, the upsampling factor, then we will get the sample from the original. Then we get the corresponding sample from the x of n. Okay, otherwise we keep zeros. This is how the expansion happens. So since this expression is little tedious or involved, let us try to write this expansion expression in a simpler way. Okay, so how do I write it? Summation over x of k. Just check whether this is n minus k times L. Okay, k equal to minus infinity to infinity. So what are we doing here? We have samples only at intervals of L. We are putting the samples of x of n at intervals of capital L. Okay, that's why we are taking those samples from there, selecting those samples from there. Remaining samples we are filling by zeros. Okay, this is how x of n is defined. Okay, with single expression. Right, this is for upsampling. Okay, so see, sometimes we may also wish to do say x of n both downsampling and upsampling together. Say I would like to change. So the problem may be change the sampling rate, sampling period of x of n t2 t dash, where t dash is equal to 3t by 2. That implies what should I do now? Need to say how do we achieve this? That means I would like to increase the time period not by say 3 times or reduce it by 2 times. I would like to increase it by 1.5 times. So I need to downsample, sample, fine, 3 times, then or like and upsample. Okay, we'll see which is to be done first and which is to be done later, and upsample by 2 times. Okay, in which sequence we'll see later. That we will bother later. Okay, so whether upsampling has to be done first or downsampling has to be done first, or any measures that we need to take care, we should see first. Right, now let us figure out the implications in the frequency domain. First of all, let us understand why should we bother about frequency domain implications. See, assume that I have a signal. Okay, so the spectrum of the signal, I will directly sketch the spectrum of the signal. Or if you say assume that there is a signal which is roughly, okay, I will try to depict. Okay, this signal is something like sin square. Okay. Okay, this is sin square signal. Okay. So 0 here and some, okay, let's not bother about exact things. And this one sample. Okay, this is another sample. Okay, this is another sample. This is one sample. This is another sample. Let me. Okay, let us put this. Okay. Okay. This is 0, minus 1, 1, so minus 2, 1, 2, okay, 3, 4, 5, 6, 7, 8, and so on. Okay, similarly this side. 2, minus 3, minus 4, this is minus 5, okay, minus 6, minus 7, okay, like this. And this is x of n. Okay, assume that there is an underlying signal. This is x of t. Okay, let this be, okay, x of t or xc of t, continuous time signal. This is continuous time signal. Okay, so this is x of t. Fine, and we have this x of n. Now, see, its spectrum, let it be, so in frequency domain. Okay, in frequency domain. Let this spectrum be how is the spectrum of sync? It is assumed that it is triangular spectrum. Okay, this is 0, minus omega m to omega m. Okay, so let this be the spectrum in frequency domain. Okay. Okay, and now what we want to do is we want to see the implication of downsampling and upsampling. See, the question is, see if I downsample. Okay, this signal I downsample. So what am I doing? I am trying to, if I do downsampling, what am I doing? I am trying to take lesser number of samples. So see, assume that in this case, the sampling frequency, see, I have taken samples anyway. So this is the spectrum of what? This is the spectrum of x of t here, right? So I will denote with same roughly, if experiment, I will try to bring in the same color. So this is x of j omega. Okay, this is a spectrum of continuous time signal. However, if we see the spectrum of discrete signal x of n, okay, or the discrete excess of t, corresponding excess of t, how does it look like? As you know, the spectrum of discrete signal, okay, if you see, what will happen? The corresponding discrete signal will repeat. Okay, it may be repeating based on the omega s. Okay, this is minus omega s and omega s. Okay, this is whole together is excess of j omega. Okay, so I hope you will be able to relate. So I am not explicitly writing those. Okay, so this one is whole together is xs of j omega. Only this is x of j omega. Okay, so xs of j omega is all together. So all together. Okay, so I'm trying to put it as a background. So the whole together is xs of j omega. Now, if I downsample it, what will happen? The number of samples I represent will be lesser than in x of n. So, because of that, what may happen? For the ability to reconstruction, that is one question. Okay, that means, see, if I use more number of samples, it is easy to reconstruct x of t from x of n. Okay, or xs of, I will use both of these, or xs of nt. Okay, so from this or this, it is easy to reconstruct back x of t if I have more samples. If I have less samples, okay, the implication is that implying difficult to reconstruct. xc of t. Okay, from reduced or lesser number of samples. In fact, anyway per second. That is reduced frequency. Okay, that is the effect of downsampling. On the other hand, if we perform a upsampling, so the problem of reconstruction, we should see how does it affect. Okay, so we will characterize through mathematical principles to what extent I can still downsample and yet I will be able to reconstruct based on the properties of the signal. Okay, based on the spectrum of the continuous time signal. Okay, that we'll see. That is one aspect. Okay, so the second thing is this first thing. Second thing, let it be I am trying to do upsampling. Same signal. Okay, I would like to take and I would like to do upsampling by 2 times. For simplicity, we are discussing all with 2. Okay, but it's not mandatory that all 2 has to come every time. Okay, so now if we do this, what is the implication? See, if I take more number of samples, is it easy to reconstruct or difficult to reconstruct the corresponding x of t? So it is easy to reconstruct. xc of t. Okay, from increased number of samples. Samples per second. These two are compared with what? These are compared with, so this is, so compared with x of n. Okay. Okay, and this is xd of n from xd of n, and this is from xc of n. Okay, so that's what you can infer from this observation. Okay, so now we will see, so in this case, in the second case, so is it just easy or you can reconstruct the signal? If you are able to reconstruct the signal faithfully from x of n, you are sure that you will also be able to reconstruct the signal from xc of n. Okay, whereas that is not the case in first, like xd of n. This implies if xc of t can be reconstructed from x of n, okay, or xs of nt, okay, imply it can also be reconstructed from what? From xe of n or xi of n. Okay? Or x of n t dash, where t dash is lesser than t. Okay? Or xs of n t dash with t dash lesser than t. Okay? Whereas, however, it may not be, may or may not be. Reconstructed from xd of n. Okay? Right? Because it depends upon the original spectrum. If the original spectrum itself is very well band limited compared to the sampling frequency, okay, then you will be able to reconstruct that. Otherwise, you will not be. Okay.